Welcome to this month's basic training video. In this video, we will discuss the various thermal imaging cameras found throughout the MCFRS fleet. There are two common cameras in use today, the Bullard T4X and the Bullard Eclipse. This monthly basic training will review the basic operations of the camera, as well as review many misconceptions on thermal imaging camera usage and its capabilities. Although you may not have the specific imager shown in this MBT, many of the same theories and techniques can be applied to the thermal imager found at your station. Camera components: lens bezel, lens, battery, electronic thermal throttle, side strap, rear boot, LCD screen, power button, zoom button. How thermal imagers work. Thermal cameras detect temperature by recognizing and capturing different levels of infrared light. This light is invisible to the naked eye, but can be felt as heat if the intensity is high enough. The hotter an object is, the more infrared radiation it produces. Thermal cameras can see this radiation and convert it to an image that we can then see with our eyes, much like how a night vision camera can capture invisible infrared light and convert it to an image that we can see. On the inside of a thermal camera, there are a bunch of tiny measuring devices that capture this infrared radiation, and they're called microbolometers, and each pixel has one. From there, the microbolometer records the temperature and then assigns that pixel to an appropriate color. The thermal imagers used in the fire service are slightly more complicated than the provided definition, and the end users require some baseline knowledge to accurately read the image displayed by the camera. To understand how and why this occurs, we need to understand the difference in active, passive, and direct emitters of radiation. A passive emitter generates no heat on their own, and instead only absorbs and releases this heat over time. The release rate will vary depending on the material's composition and density. Some examples of passive emitters would be doors, windows, beds, and other structural components. Since passive emitters only release the energy that has been absorbed, these items can be difficult to distinguish or identify when viewed through a thermal imager. If all objects in the room are the same temperature, but obscured by smoke, think like cold smoke, scanning the room with a thermal imager must occur at a much slower rate. As you can see, the objects are visible, but not readily identifiable, and it would be easy to overlook something of importance, such as a doorway. An active emitter will generate small amounts of their own energy. Things such as people, animals, and electronics are all examples of active emitters. And when present in a room full of passive emitters, these things are relatively easy to detect. A direct emitter will generate large amounts of heat. Fire is the perfect example of this. Not only does it generate a substantial amount of heat energy, but its heat and energy will heat up the other passive emitters nearby. Reading the image. We already discussed that the thermal imager receives and transforms infrared energy and light into a viewable picture that we can see. Many times, firefighters are taught that white is hot and dark is cold as the correct way to read the display. This is true, but only in the right context. The thermal imager will automatically make the hottest object in the picture brighter until the temperature reaches the super red hot feature and the coolest object in the picture darker. This means the shading of the image is all relative to what is in the viewing area of the thermal imager. These color changes occurring, even though the object has not changed color, is called thermal inversion. In order to demonstrate this, let's take a water bottle that has been sitting at room temperature and is relatively the same temperature as its surroundings. What color is the bottle displaying as? Probably slightly cooler than the surroundings, but not by much. Remember, this is a passive emitter, and therefore, in a room full of other passive emitters, it may not stand out, and you have to scan more slowly to identify this. If we take the same bottle at the same temperature and place it in a cold environment like a freezer, what color is the bottle displaying as now? Given that the surrounding environment is colder, the bottle is now the hottest thing in the screen and is showing as a hot object and brighter white, even though it is the same temperature in the last example. The final demonstration of this is taking the same bottle and placing it in a hot environment, such as a room on fire. This same bottle is now the coldest object in the viewing area and is showing as a dark object on the thermal imager. With this simple demonstration, you can see how it isn't as easy as white is hot and black is cold. The end user needs to interpret the image and the surroundings to decode what the thermal imager is really showing us. Operations of the Bullard T4X. Press and release the power button for 2 to 3 seconds to power on the device. During this warm-up time, a maximum of about 4 seconds, the device will undergo a self-check and calibration sequence. Once operational, the thermal imager will begin to display images. Please note, since the screen resolution is only 320 by 400 pixels, images will not be shown in great detail. The image may periodically appear to freeze. This is normal. This is the device going through a self-calibration sequence. This will occur as needed every 30 to 50 seconds, depending on the operating environment. The camera contains a maximum 4x digital zoom feature that can be activated by pressing the right button beneath the display screen. Pressing this button will toggle the camera through normal, 2x, and 4x digital zooms. One added feature of the T4X is the electronic thermal throttle, or ETT.
Hello, my name is Matt Elmore, and I'm the product manager for the emergency responder products here at Bullard. In this video session, I'm going to show you how to activate the electronic thermal throttle on your Bullard thermal imagers. The electronic thermal throttle is a very useful and unique feature available exclusively on Bullard thermal imagers. The electronic thermal throttle is ideal for pinpointing hotspots during overhaul, searching for overheated electrical equipment, or clarifying objects in ambient temperature situations. The electronic thermal throttle is standard on the Bullard T4 Max and the TT versions of the T320, T3 Max. It's also available as a feature upgrade on the Bullard Eclipse and can be installed right from your office computer. To activate the electronic thermal throttle, locate the 2 black buttons on the top of the imager. Press the down button, the button closest to the front of the imager, to activate the electronic thermal throttle. For the Eclipse, Locate the black cover on the top of the imager. Press the left button, the button between the R and the D, to turn on the electronic thermal throttle. When you activate the electronic thermal throttle will automatically sense the hottest area in the imager's field of view and color it blue. Continuing to press the down button or the left button on the eclipse will further engage the electronic thermal throttle and will color more of the scene blue, eventually coloring even the coolest objects blue. As the thermal throttle engages more of the scene, the blue will become lighter in hue to help differentiate objects in the scene. To lessen the amount of blue in the scene, press or hold the up button if using a T4 Max, T320 TT, or T3 Max TT thermal imager, or the right side of the cover, the right side TT button if you are using an Eclipse thermal imager. As you cycle through the scene, you'll see the symbols TT and the corresponding number in the bottom left-hand corner of the display if you are using a T4 Max, T320 TT, or T3 Max TT, or in the upper left-hand corner of the display if you are using an Eclipse. The TT indicates thermal throttle mode. The number, 0 to 100, is only a point of reference to indicate the level of thermal throttle engagement, and by itself it has no specific meaning. Most of the benefits of the electronic thermal throttle are accomplished within the first few presses of the button. To deactivate the electronic thermal throttle, simply press both buttons simultaneously for 1 second. This concludes our video training on activating the electronic thermal throttle. Thanks for tuning in and choosing Bullard.
It is important to note that the ETT and zoom feature will not be available to use in the first 8 seconds once the camera is turned on. Additionally, the ETT function will work while being operated in the normal 2x or 4x zoom modes. Another important feature of the T4X is the super red hot automatic colorization. This will automatically add yellow, orange, and red colorization to the image when temperatures begin to exceed 500 degrees Fahrenheit. Note: the maximum operating temperature of the T4X is 1100 degrees Fahrenheit. The T4X also contains the Relative Heat Indicator, or RHI. This feature will indicate the approximate temperature of the object viewed within the crosshairs. There are 2 parts to this feature. There is a set of crosshairs in the center of the display screen. There is a bar graph to the right side of the screen. Note: the accuracy of this temperature reading depends on many factors, such as distance from the object, the type of emitter the object is, and the object's emissivity, or the ability to radiate heat. Objects with high emissivity, like metals and shiny objects, will reduce the accuracy. This device can only show temperatures of solid objects. It cannot provide the temperature of clouds of steam, smoke, or other gases. Instead, it will provide an approximate temperature of the surface behind the gas. Due to these limitations, relying on the RHI to determine the need for overhaul should be avoided. It is critical to verify indicated heat levels through traditional means wherever possible and with the use of the ETT. Like most tools and equipment, it is not only important to understand how they operate, but it's also important to understand their limitations. Remember, the thermal imager is showing us thermal contrast and temperature differences. If you have a room full of passive emitters, naturally the only thing that will make them stand out is the difference in which they shed the absorbed infrared energy. This will make many objects look similar in intensity and can make it very difficult to distinguish objects or details. In this environment, it is important to scan the room slowly with the thermal imager to allow the user to better process the images. It's incorrect to say that thermal imagers can see through objects. Remember, the thermal imager can only see infrared energy. If there is a surface with low emissivity or high reflectivity, it will obscure objects behind it. Let's take glass for example. If a person moves behind a glass door, the glass reflects the majority of their infrared radiation, and they appear to disappear. Along the same lines, an object behind another object, something even as thin as a blanket, can be hidden and easily overlooked through a thermal imager. This phenomenon is called masking. They will only appear once their infrared energy heats the masking object enough to emit its own energy. This means any piles of clothing, materials, or other objects on a floor or bed need to be manually searched, and not just scanned with a thermal imager during searches. If you're in an area in which there is no major substantial thermal differences, and objects are of the same composition and emissivity, such as wood flooring and stairs, the thermal imager will present the firefighter with a two-dimensional image. This can lead to serious injury. For example, in a building with a large amount of cold smoke, fully obscuring vision, the vertical changes of a staircase may not appear to the untrained eye. Objects with high emissivity or highly reflective surfaces such as stainless steel, mirrors, glass, etc., can actually lead to reflected thermal radiation. When using the thermal imager to locate and guide a hose stream, it is important to realize that if the stream is not hitting the fire, it may be because the location you're directing the stream to is actually the reflection of the fire. Infrared energy will not penetrate water. If you're crawling across a floor and come across a puddle of water, it may appear as if a hole is in the floor. Anything submerged in the water will be unable to be viewed. Tips and tricks for using the thermal imaging camera. The viewing screen is wider than it is tall. The manufacturer recommends moving the camera in a sweeping motion to scan the entire area from floor to ceiling and left to right. While this pattern ensures full coverage, in structures with high ceilings, such as commercial buildings and strip malls, it has the potential to only view one temperature layer at a time, which can lead to misconceptions about what's really happening in that space. Remember, if everything is the same temperature in the viewing area of the thermal imager, it will all be similarly shaded on the screen. To counter this, let's rotate the thermal imager 90 degrees. This will provide the firefighter with a taller viewing space. In normal single-family dwellings, it will often cover floor to ceiling, giving the firefighter the view of all thermal layers at one time, and therefore giving a more realistic depiction of what's really happening. While discussing large open spaces, the thermal imager is critical when it comes to commercial building fires. Remember, big buildings can hide big fires for long periods of time. The larger the structure, the longer it can compensate for serious fire conditions. When these conditions finally deteriorate, they deteriorate rapidly, and often with catastrophic results. The firefighter should utilize the thermal imager to scan the ceiling space above them before moving deep into any commercial building. This can help to identify what's going on in that space. Utilizing the thermal imager in an initial on-scene report is a quick way to help determine fire location. This is especially true with the electronic thermal throttle, or ETT, feature engaged. Not only does this help to locate the fire, or any hidden fire, but it may also help locate other important size-up factors, such as truss systems, joists, obstructed ingress and egress, crawl space vents or fires, attic fire indicators, and many more. The thermal imager can be used in the search for missing persons. People naturally leave heat signatures behind them. The thermal imager is a great tool when utilized properly. When entering a room, use the thermal imager to scan the room. Orient yourself to the room. Identify areas of egress, and search open floor spaces. Beyond that, remember the basics. Rely on good, solid firefighting practices, and remain oriented in the structure. Thank you for viewing this monthly basic training video. We hope that you are now a little more familiar with the operation of thermal imaging cameras found on MCFRS apparatus, and maybe you've picked up a tip or two on how they can best be used on your next incident.